In this video, we're going to look at a particular example of Gauss's law, which turns out to be really illustrative and really important. So I have here an insulating sphere on which I have put a uniform charge density rho, which I'm going to symbolize as alpha. Alpha is just a constant, which tells you that the density is constant, which tells you that it's the charges are distributed evenly throughout the volume of this sphere. Now, remember, the only way I can do that is to have an insulating sphere. A conducting sphere would result in the charge being distributed over the surface, but an insulating sphere will allow me to put the charge within the volume. So it's an insulating sphere, and the charge density is uniform. And what I'm going to ask is what I always ask. Let's find the electric field in region 1 inside the sphere and region 2, right? So I'm going to have to do two separate integrations here, one for r less than a, one for r greater than a, r of course being the distance away from my origin. I'm going to set my origin at the center of this sphere as just a reasonable place to set it. So first of all, before we do that, let me remind you what Gauss's law looks like. E dot dA, that should be a dot, is equal to Q enclosed over epsilon naught. Now, the Q enclosed here is what's going to be somewhat problematic because as I move out from the origin, and that is as I move out from the center of the sphere, I'm going to enclose a different amount of charge. So let's handle the Q enclosed first. So as a reminder, Q enclosed is going to be equal to rho V, really, but in this case, since my volume is varying as I move out, and because my charge density is, as I move out, I enclose more and more charge, I'm going to have to do this with an integration. I'm going to have to count up how much charge I've enclosed. I've put up here a reminder of the volume element in spherical coordinates. The actual evaluation of this is not trivial if you have angular dependence. That is, if the function you're evaluating here, you're evaluating some function times the differential dv. If this function is a function of theta or phi, this actually turns out to be not terrible, but a little bit more complex. We are not going to see that in this class. We're not having any angular dependence. The only dependence we're going to see in this class is radial dependence. And in this case, it's a constant, so it's not a big deal at all. We'll see, as a reminder, we know how to evaluate the angular part of this. If there's no angular dependence, it's always going to evaluate to 4 pi. We'll see that in just a second. So what I'm going to do is I'm going to handle this Q enclosed first. So let me just put in my my charge distribution alpha, which is a constant. And I'm going to go ahead and separate. This is a triple integral, right? I've got 3 different differentials. I'm going to separate out the differentials. This will be, r squared from here. dr integral sine theta d theta integral d phi. I just rewrote this, basically. I rewrote my integral where it's obvious what my functional, or what I'm integrating over which variable. Alpha, of course, is a constant. I should have pulled that out, but we'll get there in a second. Now, what we said in class and what we know is that if I put in the appropriate limits for these, this is going to evaluate as 4 pi. There are other places to go if you want to see those limits, why those limits are the case. The derivation of this spherical volume element is something you should know, but it's not something I'm covering in this video. For the purposes here, we know that if there's no functional dependence of the charge distribution on the angular quantities, this is going to evaluate as 4 pi, which leaves me just to evaluate this. Now, what I'm going to do here is, let's pull that out, 4 pi times, or alpha, I can pull out that constant as well, the integral r squared dr. Now, if I'm talking about how much charges I'm enclosing, notice, if I'm starting at the origin and moving out towards the surface of the sphere, how much charge I enclose changes until I move outside of the sphere, and then it's reached its limit, right? Because outside of the sphere, I've enclosed all of the charge. that I'm ever gonna handle. So let me go ahead and evaluate this, and then we're gonna actually come up with an answer for how much charge I've enclosed if I'm moving inside the sphere or if I'm outside the sphere. All right, I can evaluate this for pi alpha. I get r, sorry, this should be 0 to whatever r I'm evaluating. This is gonna be r cubed over 3. This is gonna be evaluated at my limits from 0 to r. I probably should have put an r prime here to differentiate this r and this r, but I think you see what's going on. Going to be 0 at the lower limit. At the top, I get 4/3 pi r cubed alpha. You might recognize this as the volume of a sphere. That is actually where that formula comes from. It's the evaluation of this differential over appropriate limits. No big deal. So inside the sphere, though, this r is a variable. So inside, what I can say now, inside, Q enclosed is going to just be 4/3 pi r cubed alpha. Outside, Q enclosed, and this is outside, what I've called region 2. Well, I stop evaluating when I get to A, right? I'm going to enclose the entirety of the charge, which means that's going to get me 4/3 pi A cubed alpha, right? So inside the sphere, this is my charge enclosed. It is a variable. Outside, this is my charge enclosed. It's not a variable. I've enclosed all the charge I can possibly come up with. All right. So with that background work done, I'll leave this to the side so we can look at it again. Let me get another sheet. Now we're in a position to actually evaluate this integral, or evaluate Gauss's law. So right here I have E dot dA is equal to Q enclosed over epsilon naught, right? Well, I think we've seen this enough at this point in this class to where I can skip these steps. E dot dA, everywhere E and dA are collinear, and so this dot product just becomes a simple E dA. E is a constant. I can pull it outside of the integral. Just leaves me with the evaluation of the area. I know the area of a sphere, it's 4 pi r squared, so I get E times 4 pi r squared on the left-hand side. So this should be equal to that. Now I'm in a position to say, okay, am I looking at this inside the sphere or outside the sphere? Let's look inside first, just for the fact that I've called that region 1. So in region 1, E times 4 pi r squared, remember this is the radius of my Gaussian sphere, that's the radius at which I'm evaluating this, is equal to, inside the sphere I get 1 over epsilon naught from here. Q enclosed is then 4/3 pi r cubed alpha. Alright, so what can I get rid of? Well, I can get rid of the 4 pi. That's going to cancel with this and this. Leaves me with a 1 over 3 here. Look at the r's. I've got an r squared here and an r cubed here. If you really think about it, that should not surprise you, because the left-hand side of this involves an area. The right hand involves a volume. This is going to scale as r squared. This is going to scale as r cubed. What I'm going to be left with then is an r to the first power. So it looks like what I'm going to get here. E is then equal to, what do I have left? R, I was write it like this, alpha r over 3, or maybe better to write alpha over 3, sorry, epsilon naught, alpha over 3 epsilon naught r. The electric field inside for a uniform charge distribution turns out to be linear. That's interesting. Okay, so this is region 1. Let's evaluate region 2 outside the sphere. For region 2, as a reminder, I've enclosed all the charge that I'm going to be able to enclose, 4/3 pi a cubed alpha. So let's do this. Region 2. Left-hand side is still going to evaluate as this, E times 4 pi r squared. is equal to 4/3 pi a cubed alpha. And all of that is over epsilon naught, Okay, I can clean this up a little bit, clean up how it looks. I'm still going to lose this 4 pi and this 4 pi. And what I'm going to get, totally fine to do that. Let's continue that. I'm going to get E is equal to, what do I have left? A cubed alpha over 3 epsilon naught r squared here on the bottom. This is perfectly valid. I'm totally fine to do that. I didn't mean to do that. I didn't mean to take this step, but it's okay if I do. And this answer is perfectly valid. Now, let me show you what I meant to do and maybe a different way to think about this, although this is correct. Let me rewrite this step. Sorry, I got ahead of myself. E times 4 pi r squared is equal to 4/3 pi a cubed alpha over epsilon naught. Let's look at the term here, 4/3 pi a cubed alpha. What is this? What is this? This is the total charge enclosed. Well, okay, if I'm outside the sphere, isn't the total encharged closed just some total Q, which I can write like that if I want to. I don't have to take this step, I can go here, but this is illustrative to see. This is the total charged enclosed. I got that from here, right? The total charged enclosed is 4/3 pi a cubed alpha. Whenever that appears, it's totally fine for me to just sum that up as Q. What do I get then? I get that E is equal to 1 over, from all this, 4 pi epsilon naught, and then I've got an r squared still in the denominator. The epsilon naught came from here, then I've got a Q over r squared. You might recognize this is our Coulomb constant K. That means this is equal to KQ over r squared, right? So either one of these works. I like this one though, because what is that? That is the electric field due to a point charge. We've said this before, this is another illustration of it. As long as I'm outside of this charge distribution, anywhere outside of it, I see it, quote unquote see this as a point charge at the origin here. It doesn't matter that it's distributed. If I'm outside of the volume, I see this as a point charge. Why is that nice? Because if you know how much charge is on this, and I say, whoa, what's the electric field out here? You don't actually even have to go through all this. You say, Gauss's law shows it acts like a point charge, KQ over r squared. So which is better, this one or this one? Well, they're both right, so maybe better is not the right way to say it, but this one is probably more useful. Outside the sphere, it acts like a point charge. Inside the sphere, the electric field scales linearly. That's really interesting. We're physicists here. We gotta graph things. If I don't feel like I've done my job, I didn't graph anything. Let's look at that. All right. So if I'm going to graph the electric field as a function of the distance from the center of the sphere, here's radius, here's electric field. And we'll say this is A. So in this region, I'm inside the sphere. In this region, I'm outside the sphere. Right? What this says is that the electric field is linearly increasing inside the sphere. Linearly increasing. Outside, it drops off as 1 over r squared, just like a point charge does. Right? So this result we see is for the electric field everywhere for an insulating sphere with a uniform charge distribution. The electric field everywhere for an insulating sphere with a uniform charge distribution. All right, if you're watching this as part of my 1610 class, in class I started to do a slightly different problem. right? In class, I started to do an alpha R here. And what we found in class, and I would invite you to actually do that. Put an R here. This is now not a uniform charge distribution. It's a function of the radius. And redo this whole problem. What you're going to get is an R cubed here. So you're going to get an R to the 4th over 4 here. So your answer will look somewhat different. But the idea is, if inside the sphere I have a functional dependence on R here to the 1st power, I'll give you the punchline. What you get out of here is that inside the sphere, the electric field increases exponentially, or I should say quadratically. It's not linear now, it goes as R squared. And then outside it decreases as R squared. If the charge density is alpha R squared, inside I'm going to get it increasing as R cubed. So what I would recommend you do is go through this problem again with a different sphere, with a different charge density of alpha R. I'm not going to write the R here because I want to keep these pages. Alpha R, and see what happens. Go through the same process. You're still going to get 4 pi from the angular integrals. You're going to get an R cubed here, which is going to evaluate slightly differently. And just see what happens. Play around with it. This is the base where we start. After that, you can just have some fun with it.